So, I'm winding it up. It's been a good day. And now we're going to do something slightly different. We'll talk about something slightly different. We're going to talk about a language I've been working on, which is not Clojure, and it's really nothing, well, you'll see what I mean if you think about it. So, the title, Wherefore out there, LFE. Wherefore, I'm taking this from Shakespeare. That's Juliet asking about Romeo, and she's not asking where, she's asking why. Wherefore actually means why, Wherefore. That's where the word comes from. So we're asking why LFE. So we'll start here first with explaining what LFE isn't, right? It isn't Scheme, it isn't Common Lisp, and it isn't Clojure, okay? And it's probably not any other Lisp you could care to mention if you know about it as well. And the problem is, well, the reason for this is the properties of the Erlang machine we're running on don't allow you to implement these very efficiently. That's all there is for it. So what is it? Well, it's a proper Lisp. It's based on the features of the Erlang machine. It's designed to work consistently with Erlang and with OTP to run it together, and it runs on the standard Erlang VM. You don't have to do any hacks on the VM to get this thing to work. So that's what it is, it isn't, and what it is. So I want to talk a little, okay, instead of just going into saying a few features of LFE, I want to try and explain why it, quickly try and explain why it looks like it does, right? Why doesn't it look like Common Lisp or look like Clojure or something like this, right? So a little bit of history and a little bit of philosophy, the goal of LFE, what the beam means, and some properties of it, and I won't have time for implementation. So, okay, getting back to this, now we're going to talk a little bit about Erlang, because LFE is based on top of Erlang. LFE stands for Lisp Flavoured Erlang. If I'd named it today, I would have called it Erlang Flavoured Lisp instead, because the Lisp has become much bigger, much fatter than it was then. So, what about Erlang? The problem we were trying to look at way back, we're talking now 25, 26, 27 years ago. Yeah, more. Yes, 30 years ago. Ericsson had a big switch, the AXE. They still have it. It's inside some of their mobile devices. And it was a very good switch. Still is a very good switch. It made them a lot of money, but it was complex to develop and to maintain. And one of the things we were looking at in the computer science lab at Ericsson was how can we make programming these type of applications easier? I don't think the people who set us the problem thought we would end up designing a new language. So, yeah. So what are the properties of this problem domain, right? What are we looking at? Well, it's telephone exchanges, telephone switches, telecoms applications. And if you look at them, you'll find, yes, they're lightweight, they have a lot of concurrency. There are a lot of things going on in them at the same time. Back then, you might have a big switch with a few 100,000 connections going in. You might have tens of thousands of calls going on at the same time, plus everything else the switch is doing in the meantime. So we're talking about a lot of concurrency, a lot of things going on here. They must be fault tolerant. Fault tolerant in the sense that the switch is not allowed to crash. Things might go wrong, but you must be able to recover from that. If the switch goes down, that costs you an awful lot of money and it gets a very bad reputation. We've got timing constraints. Things have to happen within a certain time and at a certain time. So if talking telecoms, when someone lifts the receiver, they should get a dial tone. They should get it within, I don't know, about a tenth of a second or something like this, or some for it, irrespective of what the machine's doing in the meantime. Continuous operation, yes, 10, 20, 30 years perhaps for a good switch. Continuous maintenance, evolution of the system. You're not allowed to take it down to do things. It's not like World of Warcraft did, where they took down the machine every Wednesday morning at 3 o'clock for a couple of hours to redo stuff. You can't do that with a switch. It should never go down. And someone asked Joe Armstrong, who was one of the others who were developing Erlang, what never meant, and he said less than 4 minutes per year. That's probably quite a lot. That's probably a bit high, actually. So from these things, we looked at developing Erlang. And, well, pretty much exactly the same things went into the Erlang. So we have lightweight, massive concurrency in the system. We can do that. We can literally run millions of processes. And there are system applications in production running millions of processes. WhatsApp did it for a while. They were on one machine, they were running 2 million concurrent TCP connections on one machine, on one Erlang system, and that's at least one Erlang process per connection. Asynchronous communication. If you want a non-block so you can do things at a certain time, of course you'd use asynchronous communication. How could you not use asynchronous communication? Process isolation. Well, we're doing error handling. Things might go wrong. Processes should be able to crash, and they should be able to crash in such a way they don't destroy things for other processes, so you need process isolation. We need basis for error handling. Continuous evolution of the system. We have to be able to say load code in a running system while the system is still running. Now, running code into a system, loading code into a system, that's not too bad. But here we're doing while the system is still running and it's executing the things you're updating at the same time. Soft real time. This gets back to the timing constraints, right? Nothing can take very much long time, so the system is just not allowed to block. Going off for 5 or 10 or 15 seconds, garbage collecting the whole system is just not interesting. If you can't do it, if the system blocks for more than, say, a couple of milliseconds, it's not interesting. Right? That's just it. Now, if we're designing a language on top of these are things we really don't have to worry about in our language. These are parts of the underlying system that provides us for it. About the only thing we have to worry about here is how we receive messages. But there are other properties that are interesting from the language implementation point of view. The system provides all the other stuff for you, but here you've got things like, so we end up with, we have immutable data. All data is immutable. Okay, that's nothing very strange for a Clojure programmer, but for many other systems it is. And this immutability goes all the way down. You cannot get past this. We only have a predefined set of data types. That's it. You cannot define new data types at all. We use pattern matching for everything. If you're coming from a functional base, this is quite natural because pattern matching is fantastic. We have it built into the language. We've got built-in support for it in the machine. It's a functional language. We have a specific set of, the handling of code is well defined in the system. Okay, the system provides you with a specific way of managing code, and you cannot get around that. If you don't like it, tough. There is no global data in the system at all. That's it, right? Every system, all data is owned by processes. That's it. This is a picture of me, actually at work. 2 interesting things to point out. The thing in the middle there behind my screen, the little box with a couple of cards in it, that is a small exchange we had in the lab which we're using to test our ideas on. So this was real hardware. We could make phones ring with it. The train set, we were going to a trade show to talk about Erlang, and taking that little thing along and trying to attract people wasn't very good. There were no blinking lights. I think there was one light that went on when you turned the power on, that's about it. So we decided, how are we going to attract people? We'll have a train running, and we'll control the train by Erlang, which we did. I think I went slightly overboard here, because we had a train set. I developed an ATC system for controlling the train, so you could book passages through the system, they could block, and they wouldn't do everything for it. I even designed a tool, I didn't know about it was called that then, but I designed what now called DSL for setting things up. Colleagues did graphical interfaces so they could see on the screen where everything was, and someone else wrote a language for it. We had a lot of fun, but it worked. For 1 week it ran, actually. So yeah, so that's both work and play. Some reflections on our designing of Erlang. We were not trying to implement a functional language. We originally weren't even out to implement a language. It became functional. We started off with logic and it became functional. And someone said, oh, you've implemented a functional language. And we said, yeah, we have, haven't we? Right. Went back. We were not trying to implement the actor model. We didn't know about the actor model, to be honest. We were our very influential thing was processes, operating system processes. Then someone came back and we read a paper saying Erlang implements the actor model, so we had to go out and try and find some papers on the actor model and say, yes, we're doing that. We were trying to solve a problem. We had this problem we were trying to solve. That's what we were doing. Everything went into solving this problem. Right? And some more reflections. This made the development of the language and the system very focused because we had this problem. Everything that we were doing was into designing a language and conceptually designing a system to solve this problem. Right? It also meant we have a very good set of criteria what was going into the language, into the system. Did it help solve the problem? Yes or no? If it did, we kept it. If it didn't, we threw it out. And a lot of things went out on the way, right? So at the same time, so we're trying to build a language and a system that evolved to solve the problem, and they evolved together. So features in the language went into the ways we thought we would design a system to solve this problem. So that's why things look like they do. It also meant things became very simple. The Erlang concurrency model is extremely simple. The error handling model is extremely simple. But it's powerful enough in the sense that with those simple tools, you can build anything you want on top of it. Any form of complex concurrency model you can build on top of the simple ones. The same thing with the error handling mechanism. So just an example, the concurrency model is based on isolated processes, asynchronous message passing, and selective receives. That's it. Literally, that's it. With that, you can do anything. So the goal of LFE now we're getting back to LFE, it's a proper Lisp. We're not talking a toy here, it's a proper Lisp. It's got all the things you want in a Lisp, right, for it. It's a very nice macro package. It should be efficient to run on the Beam, the Erlang virtual machine. So it had to be very attuned to that, and it had to be able to interact seamlessly with Erlang OTP. So what we're doing is basically this from this old record by Leonard Cohen. If you haven't listened to it, please do. It's a fantastic record. New skin for the old ceremony. So what we have here, we've got the Erlang machine, we've got the Erlang system, we've got the Erlang OTP way of patterns for designing things. We want to put something on top of here, LFE, instead of LFE libraries that uses those, but uses them the way makes them look the way we want to make them look. The Beam, well, what's the Beam? It's a virtual machine to run Erlang. That's it. So it's got all the things you need, Erlang needs to run Erlang, and that's it. So all these things were mentioned before on the previous slide. They're built into the machine. It has immutable data, predefined set of data types, pattern matching, functional language things, its way of handling code, and there's no global data in it. You cannot get around that. If you want mutable data, tough. You can't do it. So now I'm going to talk some of the features of LFE around these. For a bit about the syntax, data types, modules, functions. Lisp 1 versus Lisp 2. I don't know if you guys have been into this war, which has been going since about 1960 or something like this, right? And pattern matching macros, yeah. So the syntax is pretty standard Lisp. It's pretty much common Lisp inspired, but there's a bit of schemes chucked in there as well too for it. So for example, we've got the square brackets we can use as alternative parentheses, but they're still just lists anyway. The quoting is done with a vertical bar like common Lisp. We've got these separators. We've got syntax for tuple constants and binary constants. The string generates a list of characters, or list of character codes. That's how Erlang works internally. We've got characters. We've even got syntax for a binary string. I'll explain what that is in a minute. It has these fixed data types, and this is what the Erlang machine provides us with. We have numbers, we've got atoms, a sort of equivalent to Lisp symbols. We have lists, of course, we have tuples, which are more like vectors, we've got maps, binaries, and a bunch of opaque types that are part of the system for it. So I'm just going to talk about some of them. Okay, we use Erlang atoms for Lisp symbols, but they don't quite fit. So, for example, there is only one namespace. There is no concept of namespaces in the Erlang system at all. I cannot have different namespaces. I cannot have the atom foo existing in different namespaces. There's only one foo. That's it, right? So I can't implement common Lisp style packages like this. I could do it with a bit of name hacking, with a munging of the names to do that, but then it wouldn't fit in with the Erlang system and that'd break it. Right? And the strange thing is, we've got the booleans true or false, but they're actually atoms. Right? Yeah. We've got a binary data type. Binaries are nice. So this binary is an array of bytes or array of bits. That's nothing exciting. But I can define a binary like this. The first one, just 3 bytes, 1, 2, and 3. The second one, I'm creating a binary where the first element, T, is going to be 16 bits big in a little endian style. Little endian order of the bytes. And I've got 2 4-bit fields, and I've got a 32-bit float field, and I've got a B here, which is a bit string, which might be as many bits as it happens to have, and I'll make one of these things for it. So I'm having a declarative style for creating binary data, which is very nice. I write that down, the system builds it for me, right? Which is quite nice. I have UTF-8 encoding as well too, and UTF-16 and UTF-32 for that matter as well too, so I can put UTF-8 encoded characters into my binary and it'll do both ways, and it'll just pull everything, make everything for me. Well, this is from Erlang. Erlang has a concept called records. They don't really exist, they're just a wrapper around tuples. They're just tagged tuples to make it look quite nice. So from the LFE point of view, I'd have a person tuple here with a tag person, me on it, my age, yes, and a list of properties of me, for example, right? And there's a def, well, now we're getting very Lispy here because there's a def record macro which allows me to define records, and that, when I do a def record, that will define a set of access macros for accessing my record here. So I've got creators and accessors and things like this for them, so it's very Lispy. Modules, they're very basic. They just contain functions, that's it. There's nothing else in a module except functions. If you're coming from an IO world and try to consider them as being classes, you're way overside here. There is just functions. There's a flat module space. So if I have a module called foo, there's only one module foo in the whole system. If I load in a new module called foo, I'll overwrite the other one, or delete the other one, right? They're the unit of code handling. So that's how I compile, load and delete code and upgrade code. Functions only exist in modules. I cannot have a separate functions, and the only thing I have in modules are functions. And there are no interdependencies between modules at all. Modules can come and go exactly as I want dynamically in the system. Right? This is just what the Erlang system provides. This is how it gets around the problem of being able to upgrade code while the system is running. So here's a simple little module called a ref, and I'm exporting the functions, and each function here has an arity, which is the number of arguments it has. Functions cannot have a variable number of arguments. You cannot do that. The function has a fixed number of arguments, and that's it, right? However, I can have functions with the same name and different number of arguments, and they're separate functions. So here I've got two functions add, one with 2 arguments and one with 3 arguments. So if I call it with 3 arguments, I'll get the second one. If I call it with 2 arguments, I'll get the first one. If I call it with 1 argument, I'll get an error because there is no add of 1 argument. That's just baked into the system, right? This looks a bit like Common Lisp. Modules, well, this is just how they're built up. At the back end, they end up just being a collection of functions. Okay, Lisp 1 versus Lisp 2. I don't know if you're into this, but the thing is here, depending on which Lisp you come from, symbols can have many properties. Well, one property is their value, and in some Lisp they will also have a function binding. Now, if you come, for example, from Scheme and Clojure, that's the same thing. Right? The symbol just has a value, and irrespective whether I use it in a function position or as an argument, I'll just use the value field for it. That's Lisp 1. In Lisp 2, they have a value and they have a function cell as well. So if I use it in the function position, I'll use the function cell, and if I use it in the value position, I'll use the value cell. That's a Lisp 2. Typical Lisp 2 is Mac Lisp. Common Lisp does it that way. Lisp Machine Lisp did it that way as well too. They're from that family. Scheme and Clojure just have Lisp 1s. So what do I do for LFE? Well, I have this case here. So I can have 2 functions foo at the global level, and I could define a let here, let baz equal lambda, and could call baz of 1 argument. But I think this is a bit unfair and a bit inconsistent. So why can I have 2 foos at the global level but only 1 local baz, right? So I tried to redefine baz as another lambda. I could only have 1 of them at one time. I felt that was very inconsistent. I started off like this. So we went this way instead. So I can have multiple bazes, local function bazes. I can have a baz here of 1 argument and a baz here of 2 arguments. They're both within that in scope here. And I can call the same way I can call foo of 2 arguments or foo of 3 arguments. So I can call baz of 1 argument and baz of 2 arguments. So I went with the Lisp 2 because I felt it became actually more consistent. Consistently consistent, I'll put it this way for it. And yes, I know Lisp 2 is not as nice as Lisp 1. Lisp one is not pure and more beautiful, but this I felt was consistent. I felt it was easy to work with. So yeah, so why not? Actually, I would say Erlang is a Lisp 2+, because I can have many functions called foo with different number of arguments for them. That's perfectly legal. We use pattern matching everywhere. And pattern matching is a really big win. Once you've got it, if you use it, once you've started using it, you never want to get rid of it, right? It's fantastic. The Erlang VM supports it, so we use it everywhere. We use pattern matching everywhere. It's not an extra little macro that pulled on, it's built into the machine itself. So we use inside let's. Let's not a name of variable, it's a pattern. We have a case using patterns, receive for collecting messages based on patterns as well. Everything's based on patterns here. I can have a function here. I can have a function with multiple clauses, and I use pattern matching when I call to select which clause I want to do. It's beautiful. I even got patterns in cond as well too. So you can pattern match against a cond, and if the pattern match succeeds, I can access the variables there as well. I mean, once you get going, you just don't want to stop. Some examples of functions. I've got the Ackermann function. Here I'm using the square brackets just to try and make it easier to see the arguments of the function. So here's Ackermann's got 2 arguments. And the first pattern says if the first argument's 0, I'll just take the first clause there and I'll just return plus n1. The second one says if the first one's not 0 and the second one's 0, I'll take the second clause and I'll do the third clause. So just write down. Again, I'm writing down, the nice thing with patterns is I'm writing down what I want it to look like, not how I'm going to test it. So here we have a member function which tests its first argument is a member of the list, the second argument list here. I could write in a more testing style like this. I could say cond if the second argument is equal to empty list, I return false. If the first argument is equal to the car, the second list, I'll return true, etc. Or I can write it down as patterns if I got down there, the second one. So I'm writing down what I want them to look like. I think I've got about 8 or 9 minutes left, I think, from the time. But we went another step. Binaries are fantastic. We can have patterns as binaries as patterns as well too. So this binary describes an IP version 4 packet in one go. Right? So there's a 4-bit version. There's a 4-bit header length. There's an 8-bit service type, a 16-bit total length, 16-bit ID, 3 bits of flags, 13-bit fragment offsets. There's a time to live 8. There's a proto 8, etc., etc. So this, I can create an IP packet just by writing this down. The system will build it for me. The nice thing is I can use that as a pattern. So if I get a packet coming in, I can match it against that pattern, test it, and pull apart the whole pattern in one go. That's the nice thing with using patterns for it. That's one thing that Erlang took from Erlang and LFE took from the functional world, not the Lisp world. We don't really have constructors in the same way. So this is a on the right-hand side, it builds a binary. On the left-hand side, it's a pattern which matches and pulls the binary apart. Both tests and pulls things apart. That is really nice when you get used to it. We have macros. They're unhygienic. Variables are scoped and you can't change them, so it doesn't really make that much difference. There's no gensim. That's a property of the Erlang machine underneath. If you create atoms, you'll eventually fill the atom table and the machine will crash, so you don't want to do that. At the moment, they're only compile time, but I'm working on making them, well, they're not compile time. They should be not compile time at the moment. I'm working on, well, compile time, they only exist when you're compiling. I want to make them exist outside as well too. But there we run into the problem, as I said, because all Erlang has are functions. It doesn't have this concept that many Lisps have. The system can differentiate between what's a function and what's a macro. We can't do that. We just have functions. Right? I also put a bit of safety check in here, so a bit of self-preservation. Yeah, you can redefine the core forms with macros if you want, but they'll never be used anyway. Right? So if I define a macro called cons, the system's not going to complain. It's just never going to use it. I mean, some form of limit you have to have, right? For it. So yeah, I can define macros. There's a def macro here. So I've got an add them there, which takes 2, just returns a plus of the 2 values for it. Yeah, we have the backquote macro, which is really nice. And I can define a macro average of args here, which takes a list of arguments and returns something which sums up, generates a form which sums up all the arguments and divides it by the length of the argument list. The slightly different here is the arguments that are passed in doesn't include the macro name. It's just a list of arguments. I did that at the beginning. I'm still wondering whether it should include the macro name as well, but it's a bit late to change it now. And here's the macro definition of list star, which conses together all the elements, or makes a list of all the elements except for the last one, which it puts as the last thing down there. It's just a recursive macro like that. And I can have multiple clauses. You can see in the list star there. Again, we're using pattern matching to select which clause you're doing when you're expanding the macro. And we have the backquote macro. Yeah, what do I end up with? The last thing here, a little bit of code. So this code, this is actually a rewrite of Erlang code which we ran in the lab on that little switch we were doing. So we had our own little system there for experimenting with, and okay, yeah, it's good code. We had an experimental system we could run. We were using this in courses so you could program telecoms thing, you make the phones ring, you could talk between them, stuff like this. So here we've got, this is typical Erlang style of programming as well, which has now become LFE style as well. So this is the code for two processes in the midst of making a call. So we've got the ringing A side and the ringing B side. The A side, that's the person who lifts the receiver and pushes in the number, clicks in the number. So now the phone is ringing. So the A side hears the tone in his receiver or her receiver, and the B side you hear the phone ring. And they've got two processes doing that. One side process for the A side and one process for the B side. There are actually more processes around this managing all these type of things. Right? So what can happen here? They're both going to receive and they're sitting waiting for a message. So what can happen on the A side is we can go on hook. I give up, I don't wait anymore. We go on hook and I get an on-hook message coming in there. That's the first message. What do? I send cleared to B side. The bang is just a send, it's an asynchronous send. I send cleared to B side, and I call my teleOS, which just stops the ringing, just stops the tone. That just sends messages to the switch. I'm getting messages in from the switch, I'm sending messages out from the switch. And I go to the idle state by calling the idle state function. Yes, we have tail call optimization. How can you live without tail call optimization? The other side could happen, okay, so we send cleared to the B side. If B side gets a cleared, well, it stops the ringing and the phone, and it goes to the idle state. What can also happen is on the ring on the B side, we get an off hook because the person answers the phone. And what happens then? Yeah, we stop the ringing, and then we send an answered to the A side. Just send a message to A side, and we go to the speech state here, keeping track of what we're doing. Now, when the A side gets an answered, it stops the tone, it connects the switch. So by default, by custom, it's the A side which connects the switch, so that's what the connect does. It connects the switch, physically connects the switch, so now on the A, B side phones talking to each other. And if you had a real system here, you sit and talk to each other, and we again go to the speech state by calling the speech state function. Now what can also happen here, someone can try and call us. Both the A and the B side, we get that by getting a C's message. Someone is trying to call us here. This is a tuple with the C's here. And what do? Well, we have to reply immediately. So we send back rejected, because we're busy, so we don't want to do this. We send back rejected, and we stay in the ringing A side by calling that function, and the same side in the B side. And if we get anything else, we'll just throw it away at this level here. So you notice here, the communication is completely asynchronous. This never blocks anywhere. So these two processes are always in such a state that they can respond to any message that's sent to them now. There's no synchronous calls or anything like this, and they're not. So when we get an off hook here, we're not making a call across to the B side. It's not making a call to the A side saying we've answered. We're just sending a message to it and it going on. And yes, you can get two things happening at the same time, but they'll just send messages and the system will never block. So yeah, everything is asynchronous. Notice as well too, how do we communicate with the outside world? By messages. So when something happens on the outside world, they send us a message. And how do we control the outside world? By sending the outside world a message. So we are reactive. So we are completely buzzword compliant, right? And we've been for about 25 years. So So yes. So yeah, and I just want to say, I'm not in any way claiming we were the first to be asynchronous and reactive. Of course we weren't. This was very old. But from our point of view, when the reactive and the asynchronous side came along, we said it's sort of, yeah, great, of course. How else would you do it, right? How could you not be asynchronous? If you want to make a system that doesn't block, how could you not be asynchronous? Of course you don't have blocking file I/O. That would kill you, right? Of course all I/O is asynchronous, right? Yeah, sorry, okay. I will stop here. So yes, okay, seriously from our point of view, if you're going to make a proper non-block system that does not block, that will scale, you need these type of things in there from the very beginning. And this is your base. If you want synchronous communication, yes, you build it on top of the asynchronous by sending two messages. You send a request and you sit and wait for the reply to send back instead. That's how you do synchronous communication. You don't try and put something, the asynchronous is the lowest level. It scales as well too, to be honest. So the final question, and I might almost be done in time actually. Why? Why do I do this? Why? Of course. Well, the first one is I like Lisp. Yes, I like Lisp. I've been a Lisp programmer since before Erlang. I don't know if you want to count Pascal and Fortran as high-level languages. Otherwise, Lisp was the first high-level language I learned before that, so I like Lisp. And I like Erlang, to be honest. I think it's, for what it was designed for, it's a fantastic language. It gets it right in many points. It's not a general-purpose language. It doesn't solve, you can't use, you can use it to write anything, but it's not good for everything, to be honest. But I like it. And I like to implement languages. That's my hobby. If anyone wants to talk Lua or Prolog written on top of Erlang, come by and I've got those as well too. They work. And they're correct too, and they follow the standards. So, yeah, okay, this was my own language. So, of course it seemed natural doing the LFE, right? That's why. And yeah. That's me. And here are some pages onto the LFE. So LFE is sort of taking off. The first one is the web page. I haven't done that. It was a friend of mine, Duncan McGregor, who's done the web page. He's done a lot of documentation and a lot of examples and code and stuff like this. The second one is where you'll find the core LFE system. The third one is you'll find a lot of libraries and things around that. Hasn't been quite standardized yet. There's a Google group as well if you want to get in on the chats. And there is also an IRC chat as well called #ErlangLisp. Yeah, I'm doing a flavor package for Lisps now. The old Lisp machine flavors, I've got one of those sort of working for LFE. You can't do it properly because the Lisps are different, but I've got a lot of the fun features working there. That was a lot of fun. Okay, that's about it. And I'm on time. Yes, fantastic. Okay, so thank you. Any questions if you've got time, or afterwards, or what? Take them afterwards. Yeah, I will. One. No. No, the question was, are patterns storable? Are patterns a thing? No, they're not a thing. That gets you, there are a couple of times that gets you, to be honest. But you can't do that, no. So yes. Okay.